On number 32, we're given this vector field here, F. F has two unknown constants, A and B. We want to figure out, for what values of A and B does this vector field become conservative? Okay, so I want to start off by labeling some stuff here. So there's something times I hat, something times j hat, something times k hat here. So I want to call the different components of our vector field P, Q, and R. Okay, so how do we show that a vector field is conservative? We have to check, in this case for a 3D vector field, we have to check 3 pairs of cross partial derivatives. The first pair is that we have to look at P and Q. And so we want to take the derivative of P with respect to Y, which corresponds to, j hat. And we want to take the partial derivative of Q with respect to X, which corresponds to I hat. So partial P, partial Y needs to equal partial Q, partial X. Partial P, partial Y, I don't see Y dependence here. That gives us 0. Partial Q, partial X, again, I don't see Y X dependence there. That 0 is equal to 0. Okay, kind of boring. Okay, the next pair, let's look at these two. So this is P and R, they're corresponding to the X variable and Z variable. So we want to take the partial derivative of P with respect to Z and the partial derivative of R with respect to X. Okay, so what do we have here? The partial derivative of P with respect to Z will be a x to the 9th times sine Z. The derivative of sine Z with respect to Z is cosine Z. The derivative of this with respect to X will be 10x to the 9th cosine Z, and that's 0. So what do we observe here? A has to equal 10. Okay, one more thing we have to check is this pair, which are corresponding to Y and Z. So we need to check partial Q, partial Z. The partial derivative of this with respect to Z, it needs to equal the partial derivative of R with respect to Y. Okay, so what happens here? The partial derivative of this with respect to Z will be B times e to the 2y. Derivative of z cubed will be 3z squared, so I'll write it like that. And then the partial derivative of this with respect to y, well, that will be 0. And then we just have 3 times the derivative of e to the 2y will be 2e to the 2y, so 6 e to the 2y times z squared. And so from this, 3b has to equal 6, so b is equal to 2. Okay, so at this point then, replace a with 10 and b with 2. For part B, we need to find a potential function. How do we find a potential function? F of x, y, z. I'm going to write it out in 3 different ways here. And so it's going to equal the integral of this first component, which is now a is 10, x to the 9 sine z, where we integrate with respect to x. Now we'll integrate this component, 2e to the 2y, z cubed. We want to integrate that with respect to y. And then we integrate this component, x to the 10th cosine z plus 3e to the 2y z squared. We need to integrate that with respect to z. So what do we end up with? Okay, integrating with respect to x, this would become x to the 10th sine z. Integrating this with respect to y, this will become e to the 2y z cubed. Integrating this with respect to z will give us x to the 10th sine z plus this will give us e to the 2y z cubed. Now I left out something so far. What did I leave off? We need like plus c's here, but it's not just going to be a constant. It's going to be c1 and c2, c3. where this isn't a constant, this is a function that depends only on y and z, the two variables that aren't x. This is a function that depends only on x and z, the two variables that aren't y, and this would depend on x and y. Okay, so now let us combine our answers. So what is our final answer for f of x, y, z? Is going to be x to the 10th sine z. So we see that here, and we see that down there, so that combines. And x to the 10th sine z must be part of c2 of xe. Okay, what else do we have? E to the 2y z cubed. There's also e to the 2y z cubed here, and e to the 2y z cubed must be part of c1 of yz. And that takes care of all the terms we see here. You could tack on a constant if you want to. It just says find a potential function. It says find the potential function. I should have written that as find a potential function. This will work. You know, shifted by any constant, it still works. Okay, so then finally, we are asked in part C, integral over a curve C of f dot dr. Well, we know now f, with these choices here, f is a conservative vector field. So f can be written as the gradient of little f. So we can write it like this. So we should know by our fundamental theorem of calculus for conservative vector fields, their line integrals, this equals f of q minus f of p, where, as stated in the problem, these are the endpoints here. So like this is like q and this is p, so we're going from p to q. Now, how to evaluate this? We're told that p and q are 2 points on the level surface defined by f is equal to 3. That means that f of q is equal to 3. That means that f of p is equal to 3. So this final answer here is 0. So that's how we do problem 32. Okay, for problem 33, find the potential function for this vector field. Let's just, the problem doesn't ask us to do it, but just to practice here, let's just make sure that we can see that this is, in fact, conservative. So, once again, partial p, partial y needs to equal partial q, partial x. So partial p, partial y is z plus 0. Okay, yeah, just there's no y dependence there, so that's z. Partial derivative with this respect to x will be z plus 0. Okay, that checks out. Partial derivative of p with respect to z needs to equal partial derivative of r with respect to x. And so partial derivative of p with respect to z will be y plus 2x cosine z. That needs to equal partial derivative with respect to x, y plus 2x cosine z. Yep, 2 for 2. Finally, partial derivative of q with respect to z needs to equal partial derivative of r with respect to y. What do we end up with here? Partial derivative of q with respect to z is x. Partial derivative of r with respect to y is also x. Everything checks out. So same process as before. To find our potential function f of x, y, z, we write it in 3 different ways. We integrate with respect to x of the p component here. So yz plus 2x sine z. Integrate with respect to x will give us xyz plus x squared sine z plus something that maybe depends on y and z. Okay, part 2, integrate q, xz plus 3y squared with respect to y. This becomes xyz, this becomes y cubed, plus some function that maybe depends on x and z. And finally, we integrate xy plus x squared cosine z dz. We integrate this with respect to z. xyz is equal to xyz plus x squared sine z plus some function that depends just on x and y. Okay, so we see x, y, z in all three of those parts. Great. We see an x squared sine z in those parts. X squared sine z must be in part of that C2 function. And then finally, we see a y cubed here. And then that must be part of C1 and C3. So here is a potential function. One more problem in this video set, a 2D vector field. So for this one, again, the problem doesn't ask us to do this, so you wouldn't have to do this on the test. But let's just check partial derivative p with respect to y equals partial derivative q with respect to x here. What does this give us? Partial derivative p with respect to y is 2x plus 0 plus 2y. And this would equal partial derivative of q with respect to x would be 2y plus 0 plus 2x. Great. Okay, so f of x, y, we write down two different integral expressions because this is a 2D vector field. We just integrate this with respect to x. We integrate this with respect to y. Let's see, this will become x squared y plus x squared plus xy squared plus something that maybe depends on y. This will be x squared, sorry, not x squared y, xy squared plus y squared plus x squared y plus c2 of x. How do we combine x squared y, xy squared, and x squared must live down there, and y squared must live up there? There's our answer.